Okay, into section 4.5. This is the last section in chapter 4. And we are continuing with exponential functions. And now we're going to apply it to exponential growth and decay. Now we talked about the two different graphs when we first looked at exponential functions. We said when b was greater than 1, we had exponential growth. And that looked like this, where the function was growing as x grew. And then we had b between 0 and 1, and that was the case where we had exponential decay. And we talked about these two graphs, their domains, their range, how they're inverses of one another, and all of that fun stuff. So what we want to do now is apply this to exponential growth and decay. So this is really, exponential growth is really no different and actually exactly the same as our continuously compounded interest formula. Continuously compounded interest is an example of exponential growth. Now we're just using somewhat different letters in this section. So the compound interest formula from our previous section, we said the final amount is equal to the original amount times e raised to the rate times the time. So in this section, it's the same thing except we're using slightly different letters. We're saying A, and instead of, we used the letter P when we were talking about money because it was the principal amount, meaning the original amount, the principal amount of money. Now we're just kind of more generalizing to any original amount of something. Okay, whatever it is we're talking about, population, a radioactive amount of carbon-14 that's left in a substance. Think of the O, the subscript O, as O original. This is the O original amount. And instead of R, we're using K. Those are the only difference. So this is really exactly the same as this, except we're using slightly different letters. Instead of principal amount for the beginning amount, we're using A sub 0. And instead of R for rate, we're using K. And if K is positive, then we're talking about growth. If K is negative, then we're talking about decay. So that's how we tell which one of these graphs we're looking at, whether something is decreasing in the amount of whatever it is we're looking at or increasing. So we're always going to use this formula in section 4.5. And we're going to determine whether it's growth or decay by the sign of this rate here, K. T is still time, original amount of substance, population, whatever it is, final amount here. So it's very similar to the continuously compounded interest formula. So let's look at some of these. Okay. So I'm looking at number 2 on page 504. And we're given, and number 2 has to do with the formula for population in Iraq. So we're looking at the population of Iraq in T years after 2010. So similar to what we were looking at in the previous example. T years after 2010 is modeled by the following formula. A being the final population equals 31.5 times E raised to the 0.019 T. All right, so this is very similar to the last equation we used. Notice we're looking at the exponential growth function since decay is a positive value. And in number 2 it says, what was the population in 2010? Well, this is no different than what we looked at before. So basically we're saying, what is A when t equals 0? T equals 0 is the year 2010. So once again, just like the last one, we're evaluating this function for an input of 0, so we get 31.5. And this is in millions. And just like the last one, if we wanted the population, the projected population in 2020, we would put 10 in for t and evaluate the function. Any other value that we want. So if we wanted to answer when is the population, so using this same formula, and this is not a question in the book, I'm just making this up. So using the same formula, let's say the question is when, and again, when is for what t, which is going to give you the year, right, because t is years after 2010. So for what t will the population of Iraq, given that it follows this model, right, when will the population of Iraq be, oh, I don't know, let's say 40 million. All right, so all you're going to do now is put 40 million in for the final population. All right, so the answer is you put 40 in for the final amount, and you solve the resulting equation. So this goes back to the previous section. This is an exponential equation. We want to isolate the term with the unknown in it, so we're going to isolate that part, divide both sides by 31.5, and now we have that nice property of using the definition of a logarithm to change to exponential form. So that's what we'll do here. We're saying, I'm sorry, not that way, we're going to take natural logs of both sides, right? Since we have e raised to an exponent involving the unknown, if we take the natural log of e raised to anything, we get that anything. So we take natural logs of both sides, and we say natural log of this number equals the natural log of e raised to that exponent. Again, the right-hand side just becomes that exponent. This is just a number. And then we solve for t by dividing this number by 0.19. We'll get an approximate t of, I said I made that one up.
12.57.
So about 12 and a half years after 2010. So, you know, the year 2022, 2023. Given that it is going to follow that model, which I erased already. All right, so that's an example of exponential growth. So let's look at something that's going the other way. Exponential decay. So there's no real new information here. We're just applying our knowledge of solving exponential equations to basically to some word problems, right? Using our taking logs of both sides to solve this logarithmic equation. So we're not learning any new methods here. We're just applying the methods that we've already learned and solving these questions. All right, so this is number 20 on page 505. And this says, skeletons were found at a construction site in San Francisco in 1989. So year 1989, these things were found. The skeletons contained 88% of the carbon-14. So carbon-14, if you're not familiar with carbon-14, it's an element that's in every living thing, and when that living thing ceases to live, it it loses its carbon-14 at a very predictable rate. So we can measure how old something is by measuring how much carbon-14 is left in that living thing. And that's a lot of what, we'll use this example a lot. Now, another thing that I should probably talk about even before we look at this question is something called a half-life or a doubling time. So often we are concerned with when is something going to double or triple, and when is something going to be cut in half. So let's look at that first before we go to that. So first, since we're looking at these, we'll look at a half-life first. So a half-life is the time it takes for a substance to lose half of its radioactive element, in this case carbon-14. So recalling the formula we just looked at. Right? And this is the formula we use for any exponential growth or decay. The K value tells us whether it's growth or decay depending on the sign of that K value. Well, if we want half of the original amount to be the final amount, right? If this is the original amount, then if we want half of that original amount to be the final amount, we just replace the final amount with half of whatever that, we don't care what the original amount is, we just know there's half of it left at the end. And in that way, that original amount doesn't even come into play, right? Because we can just divide it out of both sides, right? So now I can divide whatever that original amount is, I don't care what it is, it no longer comes into play with our formula for half-life. All right, so we are now looking at 1/2, right? Once we cancel that out, we got 1/2 over here, and e to the kt over here. We're looking for the time, right, that it takes to lose half of its substance. So we're going to solve this equation for t to get the half-life. So t is going to be the half-life. And solving for t here, we're going to take natural logs of both sides, just like we have done a couple of times already. So now we're going to get natural log of 1/2, natural log of e raised to anything is just that anything, and then we divide by k to get the half-life. All right, so that is the half-life. So to find the half-life, all you got to do is divide natural log of 1/2 by whatever the rate is, right? Whatever the rate of decay is. So looking at this, if we wanted to double the original amount instead of half, hopefully you're going to see that we're going through the same exact thing, and the only difference is we're going to have natural log of 2 here. All right, so if we go for doubling time, going through the same process as we just did here, twice the original amount. All right, we go through the same process here, we eliminate the original amount, we don't care what it is, we just want to know when does it double. Now we're exactly the same as previous, except this is 2 instead of 1/2. So natural log of 2 over k gives us the doubling time. And if you notice, if I want tripling time, that's just going to be natural log of 3. If I want quadrupling time, that's just going to be natural log of 4, and so on. So these are very useful formulas. If you don't remember these formulas, again, you can just derive them very easily to get them. Just let the final amount be twice the original amount here, solve for t. Let the final amount be half of the original amount here, solve for t. You get these formulas. All right, so going back to number 20, first we need to find the rate. We're not given the rate here, right? We are told that the skeletons contained 88% of the expected amount of carbon-14. Oh, actually, they do give us the rate in the problem. So given, K is given as negative 0.000121. Okay, that's given. That's the rate of decay for this carbon-14, and that's going to always be the case. Whenever you're talking about carbon-14, this is going to be the K value. Okay, so if you want to memorize that, fantastic. Otherwise, you can always derive it given whatever question we're looking at. So we're talking about radioactive decay here, so we're looking at this formula, as usual. And we're given the K value, right? K is given as that value. So we can plug that K in and say negative 0.000121 T. That's our exponential decay formula. Original amount, final amount, rate of decay, number of years. So we're told that it contains 88%. So again, we're not concerned with how much. We're just concerned with the percentage. So 88% is left, and it says how old are the skeletons. So basically we're looking for this number, and we know that 1989 is the year that they were found. That's not t equals 0, that's the year they were found. And we want to know how old they are. If the final amount is 88% of the original amount. So just like here we said half of the original amount to get the half-life and twice the original amount to get the doubling time, we're now looking for the time it takes for these skeletons to lose 12% of their carbon-14 or have 88% left, right? So just be careful with the wording. Sometimes it'll say they've lost 88%. In that case, you're going to put 0.12 here. In this case, it says they have 88% left. Okay, so they still have 88% of the original amount. They started with 100% of the original amount. We don't know what it was, but it was 100%. And now our only unknown is the T. Right? Because we can, so just like we did with half-life and doubling time, we don't care what the original amount is, that just factors out of each side. And now we're left with 0.88 equals E raised to that value. We take natural logs of both sides. E, natural log of E raised to anything is just that anything. We solve for T. And I got this one here. This is approximately 1,056 years old. Okay, so that's an example of exponential decay. These skeletons were found in 1989, and they had lost 12% of their carbon-14. So just for information's sake, I believe the half-life of carbon-14 is something like 5,700 some years. You can figure out the half-life using this formula very easily, but I think it's, if I remember, it's 5,750 years, something like that. So if they've only lost 12%, notice 1,056, our answer is much less than the half-life. That's a good way to check your answer. 1,056, much less than 5,700, which makes sense because it hasn't lost half of its carbon-14 yet. It's only lost 12%. So those skeletons are a little bit over 1,000 years old. So that's an example of exponential decay. Let's do one more. We've done an exponential growth. We've covered half-life and doubling time. And let's look at another radioactive substance. This is number 28 on page 505. And this has to do with thorium. It doesn't really matter what the element is. We're just concerned with the rate of decay and the numbers that we need to deal with. So all of these problems, we're using the same formula, right? We're using our exponential growth and or decay. We always go to that formula. And let's see here. So it gives us a half-life. So we're given that thorium has a half-life of 7,340 years. All right, that's going to allow us to find K. So now we're going to use that information to find K. So this allows us to find K. By using the half-life formula. So we know half of the original amount equals the original amount times e raised to the k times t. That allows us to solve for k. So we solve that for k. Again, we don't care what the original amount is. We're just looking for that rate of decay. So we take this and raise both sides to the, or take the natural log of both sides, right? Natural log of 1/2. Natural log of e raised to an exponent is just the exponent. And that allows us to solve for k and get natural log of 1/2 over 7340. And what do we get there? Can you give me that number, please? Should be a negative value.
Negative 0.000094.
Right?
Yep.
4 zeros?
Yep.
All right, so that's our k. And now, so a lot of these problems are going to take this form. You're going to be given some situation dealing with radioactive decay or some sort of population growth, some sort of exponential growth or decay. And then there'll be two parts to the question. You'll be given some information that allows you to find something, in this case k, because generally there's two unknowns, right? The rate and the time are two unknowns. Generally you're going to be given some information like this that allows you to find one of those unknowns, which you can then put back into the model, and then answer any further question concerning that model. So now we're going to put that k into the equation, and now we have a equals a sub 0 e to the negative 0.000094 t. Right? And now we can answer the next question, which comes up, which is, how long will it take for it to decay to 20% of its original amount? So now the question is, what t, basically what t gives a equaling to 20% of the original amount? Right? We want the final amount to be 20% of the original amount. So we form that equation. 20% of the original amount is left. When we start with the original amount, we know what the rate is, and we're solving for t. So again, we're just back to a pretty easy exponential equation. We don't care what the original amount is, we're just concerned with the percentage. We take natural logs of both sides. Natural log of e raised to anything is just that exponent. We solve for t. I think I got this one in the book. And we come up with something close to 17,043 years. And again, give it a common sense check. We were told that 50% was going to be gone after this much time. So if only 20% is left, that means our number has to be more than this. And if you think about how half-lives work, so after this much time, 50% of the original amount is left. Then of that 50%, after another 7,340 years, 50% of that 50% is gone, so there'll be 25% of the original amount left after twice this amount of time. So we have even less than 25%. So our number has to be more than twice this, which it is, so it makes sense. Okay, so you want to kind of give your answer a common sense check when you're dealing with these half-lives and doubling times.